All right, so hello everyone, welcome to this stream. So if you don't know it already, in this stream we are going to review the course material of this course, Deep Learning for Coders from FastAI. So in this stream we will start from where we left off in the last stream. So in the last stream we reviewed the multi-category portion of this notebook 6. So in this stream we will start with regression. So let's get started then. So what is regression? It's easy to think of deep learning models as being classified into domains like computer vision, NLP, and so forth. And indeed, that's how FastAI classifies its application, largely because that's how most people are used to thinking of things. But really, that's hiding more interesting and deeper perspective. A model is defined by its independent and dependent variables along with its loss function. Okay, that means there's really a far wider array of models than just a simple domain based split. Perhaps we can have an independent variable that's an image and a dependent that's text. So generally we classify this AI applications based on domains like computer vision and NLP and so forth. But a model is just defined by its independent and dependent variable with its loss function. So that means we are free to choose that independent variable of any type. It can be an image, or a text, or perhaps independent variable that's text and dependent that's an image. So if we do that, then it becomes a multi-domain problem. Or perhaps we have got images, text, and tabular data as independent variables, and we are trying to predict product purchases. So if we do that, the possibilities are really endless. So to be able to move beyond fixed applications to crafting your own novel solutions to novel problems, it helps you to really understand the data block API, which we reviewed in the last stream, and maybe also the mid-tier API, which we will see later in the book. Okay, they are saying later in the book. That means because this notebook is part of the book which has been written by the educators of this course. I forgot the name. Let me try to find the book which they are referring. It is the book is of the same name, Deep Learning for Traders. So this is the book they are referring in this notebook. Also, this all of this content is directly taken from this notebook only. They have converted this book into different notebooks. So that's why we see references of this kind. We will see later in the book. All right. Let's read on. As an example, so if you want to buy this book, you can buy it from Amazon, or else you can read it for free from this notebooks. I guess the whole notebook is available for free to read from GitHub. All right, let's read on. As an example, let's consider the problem of image regression, and this is the problem that we are going to tackle in this stream. This refers to learning from a data set where the independent variable is an image and the dependent variable is one or more floats. So that's where the regression part comes. This refers, okay, when we see people treat image regression as a whole separate application, but as you will see, we can treat it as just another CNN on top of the Datablock API. We are going to jump straight to a somewhat tricky variant of image regression because we know you are ready for it. We are going to do a key point model. A key point refers to a specific location represented in an image. Like this point is referring to a specific position in this image. This point is referring to the face, to the position where the face is inside this image. A key point refers to a specific location represented in an image. In this case, we will use images of people, and we will be looking for the center of the person's face. We will be looking for the center of the person's face in each image. Okay, that means we will be predicting two values for each image, the row and column of the face center. Okay, so that's what we are going to predict, a row and a column number. We will be using the BV connector head post dataset for this section. So let's download the dataset. Okay, the data has been downloaded. Let's also check what is inside the dataset. We have object files, something like object file, and folders named 0102. Okay, there are 24 directories numbered from 01 to 24. They correspond to different people photographed and a corresponding object file for each. We won't need them here. Object file, so we are not going to use the object file. Okay, let's take a look inside one of those directories. So inside the subdirectories we have depth.cal. We have different frames. Each of them come with an image rgb.jpg. Okay, rgb.jpg, and a pose file. we can easily get all the image files recursively with image files, get image files function. We will see it later. And then write a function that converts an image file name to its associated pose file name. But what does this pose file contain anyway? Let's look at the pose file as well. It is inside path 01. Let's get this pose file. Okay, it is just showing us the path. Do you want to display the text file? Okay, we will see it later. So first we have to get all the image files. You can get all the image files using get image files method. So let's get all the image files inside image files variable. Get image files. Let's pass the path to it. Now we have to convert that image to pose. For that we are going to create our own function. Our own method which takes the which takes the file path and format it. First get the string, convert it to string first, then get up to -7. That means it will start from here and go up to -7. So this 3, 4, 5, 6 and 7. So this will return this much portion, and then we can append pose.txt, which will give us the corresponding pose.txt. Pose.txt. Now that we have created the method, let's use it to get the pose.txt file path for the first image. Okay, we have got the pose file. Now what are we going to do? We're going to display our image. For that we are going to use pil image dot create to display the image. Can do im.save to display the width and height of the image, and you can also do im.toThumb and 160, pass it 160 to display the image. The VB dataset website used to explain the format of the pose text file associated with each image. It shows the location of the center of the head. Alright, so this they're saying that this pose text.txt file contains the location of the center of the head, the details of which aren't important for us. So we will just show the function we use to extract the head center point. Okay. Just saying that we don't need to care about what this function does, so we won't, and we'll just copy it and run it as it is. It apparently does something like generation from text, and it takes this .cal file, and after that get ctr. Okay, we don't need to worry about that, I guess. So we can use get ctr function to so this function getCtr takes the image file and it gives us a tensor back which contains two values 384, and this two values are probably the location, I guess. You can pass this function to data block as a get_y since it is responsible for labeling. So these are the coordinates of the point which denotes that it is the center of the head. Cool. So let's try to run this code inside our notebook as well. We get this coordinate. We'll resize the images to half their input size just to speed up our training a bit. Okay. One important point to note is that we should not use a random splitter. We should not use a random splitter. The reason for this that the same people appear in multiple for this is that the same people appear in multiple images in this dataset. Okay, but we want to ensure that our model can generalize to people that it hasn't seen yet. Each folder in the dataset contains the images for one person. Therefore, we can create a splitter function that returns true for just one person, resulting in a validation set containing just that person images. Okay. So for the validation set, we are going to keep a folder which contains different images of a single person, and we won't use that folder for the training dataset. For that, we will create our own splitter, something like this. Okay. And the only difference from the previous data block example is that the second block is point block. So we are using second block as point block. This is necessary so that the FastAI knows that the label represent coordinates point block. This is another kind of block. Okay, so it seems that FastAI covers a whole lot of applications. That way it knows that when doing data augmentation, it should do the same augmentation to this coordinate as it does to the images. Cool. Okay, now let's get the data block. Data block object. First, let's get the blocks and the independent variable is image. So we are using image block as the first block, and for coordinates we are going to use point block and get items. So those items are inside. We can use the function that we created earlier. Okay, we are using the image, so we can directly pass this function. We don't need to create our own function. They have already provided get image files function. Now for the y code, for the independent variable, we will use get Ctr that we created over here, which returns this coordinates. Get Ctr, and we will use a function splitter. Func splitter. What does a function splitter looks like? It splits items by result of func. Okay. So it splits based on the return value of the function that we pass it to the function splitter. So here we are passing a lambda function. And that lambda function returns true when the parent name, which means the folder, is the 13th. So for the 13th folder it will return true, and that means that folder will be taken as a validation, taken inside the validation dataset. And for all the other folders it will be false, so those folders will be inside the training set. And this time we are not using item transfer, but we're directly using batch transforms. Okay, important points and data augmentation. We are not aware of other libraries except for FastAI that automatically and correctly apply data augmentation to coordinates. So if you are working with another library, you may need to disable or data augmentation for this kinds of problem. So we are applying augmentation transform. We are resizing it to 240 by 320 and normalizing. I have an idea about what this does, but I don't know what normalization means. It was mentioned a few times, but I don't remember exactly. So I don't know what the star represents. Star function. I have never seen that before. What does it mean? Star in Python. Wait, that's a multiplication. But star in Python arguments. Okay, it's like star arcs. Non-keyword arguments, keyword argument. All right, variable length. Let's just use it. We have created the data block. Now, before doing any modeling, we should look at our data to confirm it seems okay. Right, let's get the data loaders from the data block. Call data loaders on the data block object and pass it the path. Now can check the batch. Max number is equal to 9 pixels. Six. Alright, so the points have been applied in the data set now. That's good looking. As well as looking at the batch visually, it's a good idea to also look at the underlying tensors, especially as a student. It will help clarify your understanding of what your model is really seeing. Okay, so let's get one batch and get the independent variable inside xp and dependent variable inside yb. Let's check the shape of xp and yb. (64)3, so it's a rank 4 tensor. 64 is the size of the batch and 3 means 3 channels for red, green and blue, and 24 into 320, which is the number of rows, and 320 is the number of columns. So we have 240 into 320 pixels in total into 3. And for the dependent variable we have 64, which is again for the batch size, and 1 and 2, 1 row and 2 columns for this of this kind for x and y, rows and column. Make sure that you understand why these are the shapes for our mini batches. You already saw that. Here's an example of one row from the independent variable. It's the same as before. It's a tensor point containing point. As you can see, we haven't had to use a separate image regression application. Yes, and all we have had to do is label the data and tell FastAI what kind of data the independent and dependent variables represent. The same for creating our learner. We will use the same function as before with one new parameter and we will be ready to train our model. Same function as before. Let's create the learner. We will use the same function CNN learner, pass it the data loaders and pass the resonating architecture model, and this is the new argument that we are passing. I should say a new parameter. We are passing y range. Y range is implemented in FastAI using sigmoid range, which is defined as Y range is sigmoid range. X low high return towards sigmoid of X high minus low plus low. This is set as the final layer of the model. Okay, this is set as the final layer of the model. If Y range is defined, take a moment to think about what this function does and why it forces the model to output activation in the range of low and high. So if we pass Y range is equal to -1 to 1 and apply the FastAI library will apply sigmoid range function to this range -1 to 1, and it will apply. So if our activation falls in this range, then it will apply the sigmoid range and it will be converted between the range of -1 and 1. So what it is doing is first of all applying the sigmoid. So when it applies the sigmoid, X, okay, what is X? Okay, X is the activation, this activation. It converts it to between 0 and 1. If we apply sigmoid to X, it is converted between the range of 0 and 1. After that, we multiply it by high minus low. So if the high is 1 and low is -1, then we multiply it by 1 plus 1 minus -1, that is plus. So we multiply it by 2 plus -1. We multiply it by 2, which so suppose our activation after applying the sigmoid is something like, let's say it is 1, and if we multiply it by 2, then it becomes 2, and after that we subtract the low, we add the low, which is -1. So it is basically subtraction. So after 2 minus 1, which will be 1, it will be the same. But let's say now if our activation is 0, if our activation is 0, then if we multiply it by 2, it remains 0, and 0 minus 1 will be -1. So yeah, if it is 0, it will be -1. So it will convert, this function will convert the values after if we do the multiplication and addition, this additional operation, then it will convert the values between 0 and 1 to the values between -1 and 1. Great. Just a minute, guys. let's pass y range -1 and 1. Minimum -4 and x is 4. CNN learner is not defined. Why is it not defined? Did I not? Oh, wait. The runtime got disconnected, I guess. We will have to load. We'll have to reload the whole notebook. Wait up, guys, while I reload the notebook. So while it is being loaded, let's review further. We will plot out the function in our notebook later. Didn't specify a loss function, which means we are getting whatever FastAI chooses as default. Let's see what it picked for us. So for point block, FastAI is choosing flattened loss of MSC loss. Okay, this is the loss function that it is choosing by default. This makes sense since when coordinates are used as the dependent variable, most of the time we are likely to be trying to predict something as close as possible. That's basically what MSE loss does. MSE means mean squared error loss. And if you want to use a different loss function, you can pass it to CNN learner using the loss function parameter. Note also that we didn't specify any metrics. That's because MSE is already a useful metric for this task, although it's probably more interpretable after we take the square root. We have got the CNN learner now. Let's plot the function. Let's fire up this command as well. Loss function, it is the same, flatten loss. Okay, we are going to use the learning rate finder to find a good learning rate. Let's get learn alarm find. Right, we have got the results. It is the same as the notebook. Learning rate of 1 e raised to minus 2, which lies over here. We are going to choose this learning because it is just before the dip. So let's choose 1 e raised to minus 2 as the learning rate and fine tune our model. Fine tune for 3 epochs. The freeze epochs will be 1 by default. Pass LR. We have got 2 instances running. I will have to terminate this session. Yes. I hope you guys can hear me. Two epochs are completed. Only one is remaining now. We are down to 0.0034. Generally, when we run this we get a loss of around 0.0001, which corresponds to an average coordinate prediction error of generally when we run this we get a loss of around 0.0001, which corresponds to an average coordinate prediction error of square root of 0.001, which is 0.01. This sounds very accurate, but it's important to take a look at our results with learner.show results. Okay, we will take a look at the show results after our model has been done. Training. Okay, so after 3 epochs we are down to 0.000082, and here we got 0.000036. Okay, so if I do math the square root of, if I get the square root of 0.000082, is 0.0009. Wait, they think they got a loss. Generally we get a loss around 0.0001, but here we are getting a loss around 0.00036. Alright, let's roll with it. So let's check the results. So results, pass it ds index is equal to 1, whatever that is, and row is equal to 3, fix size equal to 6 by 8. So the predictions look pretty much accurate. Quite amazing that with just a few minutes of computation we have created such an accurate key point model, and without any special domain specific application. This is the power of building on flexible APIs and using transfer learning. It's particularly striking that we have been able to use transfer learning so efficiently even between totally different tasks. Our pre-trained model was trained to do image classification, and we fine-tuned it for image regression. Okay, what's the conclusion? In the problems that are at first glance completely different, single label classification, multi-label classification, and regression, we end up using the same model with just different number of outputs. And the loss function is the thing that changes, which is why it's important to double check that you are using the right loss function for your problem. Right, so using the correct loss function is the key thing, and FastAI will automatically try to pick the right one from the data you build. But if you are using pure PyTorch to build your data loaders, make sure you think hard when you have to decide on your choice of loss function, right? And remember that you most probably want cross entropy loss for single label classification, which we used in the case of bare classification, and BCE with logits loss, which we used in case of multi-level classification in the previous stream, and MSE laws for regression, which we have used in this stream. Okay, that is that for the regression part as well. It was there was not much for regression as compared to the multi-level classification. It's considerable because inside the multi-level classification we also saw how to create a data block from scratch, or else there was nothing much to multi-level classification as well. So we are done with 6th notebook. In the future we will try to use the content from this notebook to create models on the new data sets. On this morning already I was looking at Kaggle for new data set where we can apply this content. So stay tuned for future streams where we will be applying these techniques. Alright, then this is it for this stream. I will see you guys in the next stream. Bye bye.